Hello, everybody. Thank you very much for listening to me another year. I cannot be there with you this time because I'm doing my doctoral stay in Los Alamos, New Mexico. But anyway, let me present you my work in the numerical simulation of the plasma wave interaction in electrodeless thrusters. So, this is more or less the same introduction I had last year. Electrodeless thrusters are novel devices in the electric propulsion family and they promise quite interesting advantages. You have them here. Now, the principle of operation is basically the plasma heating and the neutral gas ionization in the source by the radio frequency coupling of the waves produced by an external antenna in the case of a helicon thruster like this one. But we also have other methods like waveguides, coaxial cables. In any of these methods, the electromagnetic wave interaction with the plasma is key to the working of the device, to the performance of the device. And this is something we have to understand better because despite all these advantages that I told you, the current efficiency is really low. And this is a huge problem because classic devices like Hall thrusters can achieve like 50% efficiency. So if we want to compete with them, we have to get to those efficiencies. Now, there are two main approaches to the wave interaction problem. We have our engineering full wave cold plasma algorithms. These are 2D axisymmetric, but I think we can make them 3D even in pretty soon probably. This is like our workhorse engineering models. We use them for study of full thruster with part of the plume. We use them every day to analyze the performance of the device, understand better the losses that we have. Yeah, and they're lightweight, so we can run them in our computers in just a matter of hours if we are going to couple them with the plasma transport, which is a capability we had since recently. This is going to take maybe some days, but less than a week. We can analyze a thruster that way. So I will not go into the equations, it's not worthy. The other thing I wanted to talk about are the electromagnetic kinetic algorithms. So the problem with these full wave codes is that they are really lightweight, but they are losing a lot of physics. So we are lacking a lot of phenomena that we simply simplify and kill. And we are losing a lot of information by using them. So if we want to understand every detail of the wave interaction, we need kinetic codes. The problem with this is that they are really, really heavy, orders of magnitude heavier than the others. And we have to generally rely on lower dimensionality models and simplified configurations to study like little academic problems, but this is giving us a lot of information so we can understand better the physics. So this is like a summary of my thesis, the two main blocks that we have in them. All right, so regarding first block, this year we got publication in Q1 journal. This is a helicon thruster, so this is the axis of symmetry, this is the source, and you can see that the domain is much larger than the source. So the source is just a small part. This is because we wanted to include this green line here, which is called the electrocyclotron resonance. And it's a really relevant transition for the waves. So what we have shown that was not reported before, we have shown in this work, is that this electron cyclotron resonance surface is an excellent confiner of the electromagnetic power. In these plots here you can see the phase. You can imagine a wave traveling from the source, so you can see the wave fronts. And what we see is that the electromagnetic power is not able to reach downstream the electron cyclotron resonance, which is a good result, nice result that we got from this work. Now, for the conference that we are going to attend a couple of days from now, we are presenting couple simulations. So these are static simulations in the sense that the plasma density is provided and then we study how the wave moves through that plasma. But here we are coupling our wave solver with hyphen, which you may have heard about it. It's a hybrid particle in cell plus fluid code. We can solve for all the plasma profiles like the plasma density, the electron temperature, all the currents, performances, thrust, all this considering different processes like ionization, inelastic collisions, plasma wall interaction, anything you can think about. And also this is giving us the performances and the thrust of the device, which is the most interesting part of all the study. Now, a new feature for this study, and we hope that we will have also another journal publication really soon, coming from this conference, is that we are using a new finite element wave solver, and we are happy with this. This has improved a lot the performance of our previous wave solver, which was finite difference, and also the accuracy. We have some important gains. Okay, so let's go to the second part, to the kinetic part. This is the work I'm doing at Los Alamos. And I would say we are working with the state-of-the-art algorithm for peak. So I guess you already know, but peak is a standard for plasma physics when you want to consider kinetic effects. It's called, well, it means particle in cell. Maybe my colleagues have already talked about it. So the novel part of this algorithm is that it's implicit. So we work daily with explicit peak codes at our group, and some people are developing really nice explicit codes, but this one is implicit. So this means it's more difficult to implement, but it also has several advantages. So we are using a Jacobian free Newton Krylov solver, and one important feature about this algorithm is that our unknowns are no longer the particle positions and velocities, but the electromagnetic fields. So this means that we can select delta t based on the fields. And in general, we can increase a lot the delta t that we use. And this is important for velocity of the algorithm, for speed, of the algorithm. And also, this allows us to have exact charge and energy conservation, which are good properties for stability and for accuracy in long-term simulations. Like the steady-state operation of a thruster is an exemplary problem for this kind of long-term simulations in which you don't want any artificial electron cooling or electron heating, and you don't want finite grid instabilities to destroy your simulation. Those kind of things are important and can be achieved with implicit algorithms. Okay. Now, continuing with this discussion about explicit versus implicit algorithms and high performance computing, one problem of explicit algorithms is that they are generally memory bounded. So I am not going to go into details explaining this plot, but what this means basically is that maybe you think that your operations, your actual multiplications, additions, divisions are taking all the time of your algorithm, but it's not true. The most expensive part, many times, it's just the memory fetch. So most explicit algorithms nowadays are memory bounded, while for an explicit algorithm, for each memory fetch that you do, because you can increase your delta t, you fetch memory every time step, but you do many more operations per time step. So this means that you are no longer memory bounded, you are compute bounded. Basically, this opens a possibility to use acceleration like GPUs, massive parallelization, because it's much easier to increase your computing power than your memory bandwidth. We are already exploring this. So we're using Julia for the library we are developing, and we have started looking at some Julia libraries that provide high-level abstractions that make your life really easy, because until like few years ago it was really difficult to use GPUs. So people usually hate using GPUs. Now, because the machine learning community and the new supercomputers like the exascale supercomputers that are coming online this year, all of them are using GPUs. This is becoming much easier. So now we have high level abstractions that are, yeah, like making your life really easy. And also Julia. Also Julia, this is one of the points I wanted to highlight. Julia is a really expressive language. It's high level, but it provides you with low level inspection tools, and also it's really performant. So it's compiled just in time, and the community is quite large right now. Many people is starting to use it, and you have almost any library you can imagine to develop your code in Julia. So we will continue using this. I would say that without Julia language, it would have been impossible for me to develop the electrostatic code that we have right now in more or less a month and a half that I've been working here. Okay, so besides finishing the big code, we have to make it electromagnetic, which it is not right now. We only have an electrostatic version. We also may go to higher dimensions. The group I'm working with has a lot of experience, and yeah, it's going to be interesting to collaborate with them. And also, of course, we have to apply all we are developing to electric propulsion problems. And lastly, I would also like to continue developing my finite element solver. So it becomes like an engineering tool that anyone in the group can use. We want to include new materials, new antenna models, and there are already a couple of projects within the group that will be interested in using the code. So I want to make it user friendly and available to anyone. So I think that's all by my part. If you have any questions, I think I didn't write here my email, but it's this one. And thank you very much for listening. I hope the other talks are great. And see you pretty soon when I come back. Bye.